Hey guys, welcome back. So today I brought home this 5,000 watt Baldor generator, and as you can see, it has an issue. It stopped making power. Now, I did not take any of this apart. This is how it came. The previous owner is actually a subscriber and has watched a lot of my videos. So when his generator stopped making power, he took it apart and ran a lot of the tests that I would have done, and couldn't conclusively prove what the problem was other than the stator seems to be good, and most likely there is an issue with that rotor. So, worst case, the power head is bad, but I have a good, genuine Honda GX270, and most likely that is compatible with one of the other power heads I have up there on the bench, so we can repower this. But before I tear this power head off and just throw it away, I do want to conclusively figure out what is wrong with it. Potentially it could be fixed. So let me set up a little bit better. I want to get that stator up on the bench. We'll run a few tests and go from there. Visually, this stator looks brand new. If you look at the lacing going around, none of it's broken. There's no signs of overheating. And same with the wiring. There's no hot spots, and there are black wires, but that is just the color of the enamel. It's nothing to be concerned about. It's like that on both sides. I mean, this thing looks to be in good shape. Now, another check I like to do is to just look down each of these slots at the insulating paper, making sure there's nothing burnt. And in this case, there's not. So no smoking gun here. Just going to break out the multimeter and see what that has to say. All right, to do these tests, just put your multimeter into ohms and touch the leads together. You want to find out what the internal resistance is of your meter. In my case, it's 0.1 ohms. So any reading I get, I can subtract that from it to get the true value. So I'm going to start with this winding here. This is actually a brushless generator, and this winding is what connects to the capacitor. Now, I don't know what the value should be, but on a brushed generator with an AVR, usually I see around 1.4, 1.5. In this case, we're at 1.1, 1.2. So I would say that is most likely good. Let's just check it to ground, make sure there's no connection, and there's not. So I think that winding is good. Up here, we have a 9-pin connector, which feeds the control panel. Now, 9 pins seems like a lot. Usually, there's just 2 legs going up to that panel, and each leg requires 2 wires, and then you might have an extra for ground. So at most, you'd have 5 wires, not 9. And I can see just looking down here that actually these 2 pins have nothing in it, but we do have 7 wires in here. So I guess the question is, why do we have 7 wires for 2 legs? Potentially, this has 3 legs in it. Why, I'm not sure, because this is not a 3-phase system, but we'll figure that out later. Let's just test the resistance of these and see where we're at. So this one that's all by itself, I'm guessing that that is a ground, which it's not, but there is a ground wire that comes out on top here. And that is a ground connection, so that's fine. Let's check these 2. We get 0.5. That seems fine. Let's just check that to ground. We're good. I'm just going to move down to the next 2 pins. Nothing there. We get a connection there. So 0.5 again. I'll check it to ground. Seems fine. Then we'll check what appears to be leg 3. 0.5. and no connection to ground. So, I mean, those seem like good readings. Nothing is shorted to ground. Now, that doesn't mean that they're not shorted to each other. So, one way we can check that is just by connecting one wire to one of the legs. In this case, this is the leg that feeds the capacitor. Then we'll just check each leg. And there's no connection from here to any of the other legs. Check this one. We're good there. And we seem to be good. I'm not seeing any connections to ground or to adjacent legs. So the stator does appear to be good, but I'm going to bring out the high voltage tester and we'll just double check. For this test, I'm going to use this insulation tester. This was actually given to me by Rob. He owns a small engine repair shop not too far away from me, and he happened to have an extra and sent it my way, so I appreciate that. Thank you, Rob. This insulation tester can go all the way up to 5,000 volts, and these legs are not going to see anything near that. So I did set it at the lowest setting, 500 volts, which is at least double, if not close to 3 times the voltage that'll be in these legs. So I've got one lead connected to the ground right here. And I'm just going to go through each of the coils and make sure there's high resistance. So we're already at a gigaohm and climbing. So there's no issue there. Let's check leg 1. We're already at a gigaohm, no issues there. Check leg 2. And no issues there, approaching 2 gigaohms. Leg 3. Same thing. We're at 1.4 gigaohms and climbing. So there are no connections to ground. Let's check all the legs now to the adjacent coils and make sure nothing is cross-connected. So from the excitation coil to leg 1, we're at a gigaohm. That is fine. Try leg 2. No issues there. We're at 1.2 gigaohms and climbing. And leg 3. A little bit slower to climb, but we're at 1.4 gigaohms, and that should be fine. Let's see if I can do this without shocking myself. So I've got one lead. I'm actually using the lead on the multimeter to to get a connection into leg 1, and then we have the high voltage tester connected to that. And the other lead is in leg 2. No issues there. We're at a giga-ohm. We'll check leg. Actually, I just checked leg 1 to leg 3. Let's check leg 1 to leg 2. And we're at a giga-ohm, so we're good there. Then we'll check leg 2 to leg 3. And we're at a giga-ohm and climbing. So that's good. We've tested all the combinations between the different coils. Nothing is cross-connected. So I can pretty conclusively say that this stator is good. And probably the first thing to check on a brushless generator when it stops making power is the capacitor. It's a very common point of failure. And before you do this test, you want to make sure it's discharged. So grab a screwdriver you don't like and just short out the terminals. Now, I've already done that to this and this one here. This was replaced in part of the troubleshooting just to make sure it wasn't a bad capacitor. And even plugging in the new one made no difference. There was still no power output. Anyway, we'll start with the new capacitor. It is rated at 30 microfarad plus or minus 5%. We're at 29.45 microfarad. So that seems to be fine. We'll check the one that came with it. This one looks good too, 29.43 microfarad. So no issues with the capacitors. Hopefully you can see this okay. It was kind of hard to get the angle, but I wanted to point out this rotor design is very unique. I have never seen one like this. Usually there's a rotor bolt that goes through to hold everything onto the tapered shaft, but in this case, it actually secures down here, and you can see that is loose, so that'll have to be tightened back up if we get to that point. And the second important thing to point out here is that this looks to be a very high quality rotor. I don't think it was made overseas. Generally, this coil is not coated in a resin. And it should be, because these things spin at 60 times a second. And if they're not coated, the wires move and vibrate, and eventually one will break. And that's what I normally see, is a broken wire where it connects to the slip rings or something else, like in this case a diode. But I've already looked over all the wires. I don't see any that seem to be loose or broken, and I don't think we're going to have an issue in here per se. Now, these are a little bit tricky to test because it is brushless. There isn't a great test point, but I think I can test it through the diode, because my multimeter, when I test for resistance, it does send voltage in to see what the resistance is, but a diode needs usually around 0.6 or 0.7 volts to conduct. And my multimeter does not even come close to that. So I think if I hook up the multimeter like this, it won't be testing the resistance between the diode. It'll actually be testing it through the coil, which this diode is connected over here. And then over here, there's also a piece of metal that connects it to this pin. And these two wires are the wires coming from the coil. So I think that would be a good test. Now, the other variable here is that we have what looks to be a metal oxide varistor right here. And that is used basically to clamp down when a surge occurs. And when I say clamp down, it's basically, this is a variable resistor. And under normal conditions, the resistance is pretty much infinite, which means you can kind of pretend like it's not even there. But if there's a surge over a certain voltage, then this will absorb some of that surge, protecting, the coil. And that is connected up on the other side. There's actually two black wires. They're hard to see. They run up on the side here, and they connect to these two posts. So assuming that varistor is good, when I check the resistance here, that should not come into play, nor should the diode. The only value we should be reading is what the resistance is of this coil, which I don't know what it should be, but most rotors have a resistance somewhere between 40 and 70 ohms. And on this style generator, it is actually usually lower, like around 4 or 5 ohms. So if I see anything between 4 ohms and 70 ohms, I'll be pretty happy. So let's get the multimeter out and see where we're at. We're at 0.1 ohms. That is a dead short. So that's an issue. I mean, that's essentially like going like this. So the question is, where is that dead short coming from? It could be the diode, the varistor, or the coil itself. Let's just try this again to ground. So there is no short to ground, which is good. But I don't think I can do any more testing with this in circuit, or the varistor for that matter. But let's start with this. I'm going to heat this up and see if I can't pull that wire out. I mean, I could just cut it, but let's try doing it the right way. Yeah, I don't think this iron's hot enough. I'm going to try adding a little bit. Sometimes that helps. And it did. So the rotor is coming in at about 2 ohms. It's hard to get a good connection here. So, I mean, that seems low, but it's definitely not a dead short. So that might be okay. Now we can also check the diode. Maybe. And that is a dead short. Let's try it the other way just to make sure. Yeah, it looks like a dead short in this direction too. This is really weird. As soon as I disconnected the diode, I tested it and I got a dead short in both directions. But now when I test it, I'm getting what I expect, which is no voltage drop one way and voltage drop the other way. So I'm not sure what's different, but this is behaving differently now than it was a minute ago. And by disconnecting that, we now get what I would consider a fairly healthy ohms reading. Actually, we'll measure it this way, or maybe that way. So about 2 ohms from the rotor. And if I measure the resistance through the diode, it should be very high, if not... Yeah, so we're talking 4.7 million ohms. And open. So when this was connected, we were getting a dead short. So how could, by disconnecting that, the dead short went away? When I tested the diode initially, I showed a dead short, and now everything's fine. I would say this diode is very, very suspect. All right, so I reviewed the footage. I just wanted to make sure I wasn't crazy here and potentially touching this while doing the test, thinking I have a dead short, because it is. And I was not touching that. So the only other thing I could see that I was doing is that I did scrape this, trying to get some clean metal exposed so I could get a better connection. And when doing that, I was pushing this tab. So I tried to replicate it just by connecting it like this. No issues. I push down. No issues. But if I come at it the other way, no issues. And then I'm going to push toward you a bit. Dead short. That shouldn't happen. So there is an internal issue with this diode, and I think if I replace it, this might work. So let's see if we can get it out. It's pretty loose. It's like S1362 0733 India IER. And that tells you the direction. So we have something to go on. I'm going to go online and see if I can't find another like this. It's been about a week since the last clip, and there's good news and bad news. Probably more bad news than good. Anyway, I'm about to go on a rant, so if you don't want to hear it, skip ahead 3 minutes. But it's important to understand the direction that I'm going to take on this. So we'll start with the good news. I found a document published by Baldor generator on how to test the rotor. And it basically was in agreement with the way I tested it. And they also listed the resistance values for a healthy rotor as being between 1 and 4 ohms. And we got 2 ohms. So if there was any question as to the health of that rotor, that question is gone. It is a good rotor, 100%. And we kind of knew that because the tests on this diode showed that this was the problem. So when I removed it, I thought it was a slam dunk. We had a manufacturer mark, we had the polarity, and we even had the part number. So even if Baldor didn't supply this part, I could just go to the manufacturer and get the equivalent part, or at least find a data sheet to locate a part somewhere else. So I went online, searched for this part number, came up completely empty. Luckily, that Baldor document that listed how to test the rotor had the Baldor part number. So I looked that up and came up empty as well. So it was at that point I decided to call the tech support listed in that document and was shocked when Generac picked up. Apparently Generac purchased Baldor back in 2014. This generator was made probably in 2011. And the person that picked up at Generac, once they found out what this was, immediately said, that's an industrial generator. We don't support that. But you can call this other vendor and they service these generators on our behalf. So that's what I did, and was greeted with a message on their voicemail system stating that they're not answering phones due to the pandemic. But to their credit, they did leave an email address that I could write to, and within 24 hours they responded. And their response was basically they have no idea what part this is, and they don't sell it. They can't give me the specs on it. They don't know. So that kind of left me with my mouth open. Not sure where to go, but I did find the manufacturer who makes this by just looking at their logo. It is made by a company called Vishay. So I did go to their site, looked up this part number, came up with nothing. So I did email their tech support a week ago and never heard back. So starting to think I'm kind of on my own on this and really not sure the direction to go, at least for a few days. And I did end up calling Mauser Electronics, gave them this number, and they had the same response. They had no idea what this was and could not recommend a replacement for it. So then I reached out, or I used my lifeline and reached out to someone, another YouTuber. I'll put his channel down in the description. He has a lot of great generator fix videos, and he's big into electronics. He's a major contributor to the website Smokestack and also posts videos repairing circuit boards. So I asked the question to him about this diode, and he kind of confirmed what I was thinking, was that without the data sheet, it's going to be hard to replace this with the right part. You know, even if I can find one that physically is identical, are the characteristics the same? You know, is this a standard diode? Is it an avalanche diode? Is it a Zener diode? There's probably 26 different types of diodes, and within each type, there's probably hundreds or thousands of variations. So it was kind of a shot in the dark ordering a new diode. And it was at that point I kind of decided, fine, we'll just take the generator head off, forget about it. We'll put on that other generator head that I showed at the beginning of the video. But it's not quite that easy because this stator has 3 legs in it. And I still wasn't sure why. So I looked at this panel more closely and realized why there's 3 legs. There is a 120 volt outlet here at 40 amps. And each leg on that stator only outputs 20. So definitely 2 of those legs have been paralleled to do this. And some generators can do this, but they have a switch to switch between 120 volts or 240 volts. And when you switch it to the 120 only, it puts the two legs in parallel to get those 40 amps, but it basically deactivates the 240 outlet. This one can do both at the same time, which is pretty cool. But if I wanted to use that other power head, I would definitely have to eliminate this and do a bunch of rewiring. Not to mention there's a proprietary connector in the back, which would most likely have to be eliminated. So it's not as straightforward as I initially thought. So I started digging a bit more. I did go to this manufacturer's website, Vishay, and even though I couldn't find any cross-reference to this diode, I did find in their thousands of diodes that they sell a series that matches this dimensionally perfectly. So if I had to bet, I would say that those diodes are the same type as this one, but I don't know for sure. But that's what I'm going with. So I ordered one of those diodes and got the maximum rated one I could. So it'll do, I think, 25 continuous amps. It'll handle surge amps, I think, in the 270 amp range, and it'll handle voltage in the 1200 volt range, which is definitely overkill for this rotor, and hopefully that will solve our problem. Otherwise, we're going to have to take it all apart again and go to plan B, which is rewiring this and putting that other power head on. So it's going to be a few days before I get that new diode. I really only have two housekeeping things to do. I need to tighten that bolt on the rotor, and the bottom rail where the stator mounts is rusted pretty bad. So I'm going to get some fresh paint on that now. There's no better time than when that stator is off. Usually, to torque down the rotor bolt, I'll just remove the spark plug, bring the piston to the bottom of its travel, fill a cylinder with rope to lock up the engine, and then just with the torque wrench, torque it to about 22 foot-pounds. In this case, that's not going to work for two reasons. One, the top of the head where the spark plug is way down there. It's almost impossible to fill that cylinder with rope without removing some of this stuff. And the second reason is I can't get a socket on that, so there is no way to torque that with a torque wrench. And as it is, I can't even get the closed end of this wrench onto that bolt. So, I guess the plan was to pull the blower housing off and put a strap wrench on there and just snug it up. But I think there's a better way. I am going to remove the spark plug just so there's no compression. I'm going to get the starter recoil off. I'll get the torque wrench on the flywheel nut and torque that to 22 foot-pounds while holding the bolt from turning. So that should roughly translate into a bolt that's tightened to about 22 foot-pounds. I'm not going to go too crazy on this rail. The rust isn't that bad. I think the worst of it's just on this lip right here. So I'm going to clean this up with a wire wheel. We'll just get all the loose bits off and just put a light coat of paint on it. New diode showed up today, so let's get that installed and then put this thing back together. You know, in my head, I imagined a million ways that this could go wrong, and it still might, but that was the most critical part, and it looks like we have a good connection, so I think we're ready to put this thing together. Because the stator and the end housing are separate pieces, it's going to be a lot easier to tip this generator up vertical and just let gravity kind of work to your advantage, holding that stator in place while everything is bolted up. So before I can do that, I do need to drain the oil. Otherwise, it's going to leak out of the breather. I don't have the torque specs on these bolts. Usually 80 inch-pounds is plenty. I'm going to start with 60 and see how it feels. I only went to 70 inch-pounds. I felt things potentially flexing, and these bolts are quite a bit longer than normal stator bolts. So I think I'm going to call 60 good. I'll double check the torque later on, but I've gotten ones from the factory that were not much more than finger tight, so I think we'll be okay. Before going any further, now is a good time to pull the engine over. The spark plug is still removed, so the compression won't be fighting me. And really, what I want to see is that the engine spins freely and that the rotor is not making contact with that stator. And we're good. There's really not too much more to do. We're kind of in the home stretch here. We just got to tighten down those stator bolts, reinstall that capacitor, put the outlet box on, and do a bit of wiring. And we should be good to fire this up. But before I do any of that, I'm going to put some oil back in that engine. This grounding wire here just connects to the body of the stator and then runs down to the frame. But with all this paint that I put on there, it's not going to make a good connection. So I'm going to take a bit of paint off and then we'll bolt this in place. So what do you think? Is it going to make power? Personally, I think it's going to need a little help. With the diode the way that it would have sent AC right into that rotor, and the residual magnetism would have been scrambled, and most likely it's scrambled to the point where it will not self-excite on its own. But let's get the engine started and see if that light comes on. Guess I was wrong. Power came right on, and the voltage seems pretty good. We're right at 120 volts. Now, the hertz were coming in all weird. I mean, I can tell by listening to the engine that the engine speed sounds pretty good. You know, most likely the power output is just a little bit dirty, causing some confusion with that kilowatt. And I've seen that before, mostly on brushless generators like this one. So I'm going to get the inductive tach hooked up. We'll restart it, just double check that engine speed, and if we're good, I'll just put a load on it, 1500 watts, and see how things go. Let's try this again. This tachometer I've actually been having issues with recently, so hopefully it'll work at least one more time. it had absolutely no issues handling that 3,000 watt load. And the no load engine speed was at 3,710 RPM, which is just a touch over 61.5 hertz, which is perfect. And once it was loaded up, voltage was around 120, I think 0.7, and the kilowatt could then measure the hertz, and it was dead on at 60 hertz. And I think that is fairly typical. When there's no load on a brushless especially, the power is quite dirty. And then once you put a bit of a load on it, things clean up pretty well. So I'm going to break out the oscilloscope. We'll hook that up, just get a visual on that output. I moved over into the shade here so we have a chance at seeing the display on the oscilloscope. Let me get the generator started and we'll check out that sine wave. Now you can see it's pretty dirty. Let's put 800 watt load on it. Yeah, still not great. 1500 watts. Now 3000 watts. All right, guys, and that is pretty much it. I mean, really the only thing left is to drop the tank in place, bolt it down, but I think I'm going to end the video here. I mean, this thing, the engine sounds great. It's making power. Granted, dirty power, but that is the nature of the beast. This is a brushless generator, and that is what the output looks like on these. So, if you have a generator that's brushless, I would consider carefully what you're hooking it up to, because it can definitely cause damage, with that sine wave output as it is. That said, if it's an emergency and you need power, it'll do the job. But again, just be careful how you use it. Anyway, I hope this video helps someone. Thanks for watching.